Hi guys. As promised in class, here's a video where I'm going to flesh out some of the details of projectile motion that we had started or that we were working on in class, and then that'll get us ready for some practice problems. So just to remember, we're talking about projectile motion. And so we've got an object that's moving through space acted upon only by gravity. That's what makes it a projectile, if you remember. And we said that in this case there are three basic rules, three main rules, and that's that the x velocity is constant, just to remember, y velocity changes at negative 9.8 meters per second squared, and then finally this interesting one, which is x and y velocities are independent. X and y velocities. Another way of saying is don't affect one another. I should say one another. So these are three basic rules that govern projectile motion, just to remember what we said. So in the x direction the velocity is constant, in the y direction the velocity changes at this rate, right? And this is of course the acceleration due to gravity, g, and the two are independent, or they don't affect one another, which is, we noted that's sort of an interesting idea, but it's an idea that we can use to do some interesting calculations. So then we got on to say, well, let's take a look at 1 and 2, and what does this mean in terms of our math? What's the significance of that? And we said that we have two equations that we're going to use for distance. One that describes distance in the x direction, which I'll call delta x, and one that indicates distance in the y direction, which I'm going to call delta y. So our two equations that we'll be using over and over again. The first one is for the delta x, and since x velocity is constant, I can just use the constant velocity equation, which is delta x equals vx times t, right? This is just distance equals rate times time, right? Back in your younger days, you would say distance equals rate times time, and that's all this is, right? This is a constant velocity equation. And since it's constant velocity in the x direction, we can use that equation when we're in the x direction. But in the y direction here, we have acceleration. So our second equation applies to the y direction, delta y. And what we're going to say here is that if we want a delta y, we need to use the acceleration equation. So that's v initial y times t plus 1/2 gt squared. Okay, so this is our acceleration term right here. That's acceleration, and this is the distance in the y direction. So this is one of our kinematic equations. We'd called this before a kinematic equation, and that applies to the y direction. All right, so we'd been working on some problems in class. We'd started some problems where we were using these equations, and I want to do one such problem right now to make sure that we understand what's going on. So here's a classic problem. Let's imagine we have, I don't know, like a table. This is a tabletop. Okay, that's a table, and I guess this is the floor. And we have a ball that's rolling off of the table. So here's a ball. That's not a very spherical ball. It's a little bit better. So here's this ball, and it's rolling off of the table. And it's coming off the table here with some velocity v, and I don't know what that velocity is. That's what we're going to find. But I know that the table is, let's say, 5 meters high. And I know that when the ball comes off the table, it's going to take this, what we call parabolic trajectory. It's going to go like that. Wow, that's really bad. Slightly better, I guess. So it's going to go down 5 meters, and then when it lands, it's gone a horizontal distance here of, I don't know, let's say 8 meters. So what I'm asking here is what's the velocity? Or actually, I'll ask it a different way. I'm going to ask, with what speed does the ball roll off the table? In other words, I'm looking for this, right? I want to know what is the v with which it rolls off the table. So with what speed does the ball roll off the table? So let's think about this a little bit. Let's see if we can figure out how we're going to approach this problem. So I need to find v, okay? So let's first ask ourselves, well, is this v, is it a vx or is it a vy, right? What direction is the ball rolling? Well, this is rolling off this flat tabletop, right? So it's an x velocity. So it's this kind of velocity. And so I can say delta x, I'll do this in a different color. I'll use green. So maybe I'll say delta x, come up with a better green than that, maybe. Delta x equals vx times t. And so I'm looking for Vx. Well, I know delta x, right? That's 8 meters. So I can say 8 equals V, that's what I'm looking for, times t. So if I can figure out what t is, I can go ahead and solve for V. So then I ask myself, okay, well, what in this problem determines the amount of time the ball is going to be in the air for? And if you think about it, the only thing that matters in this problem is how high the table is. The delta y, right? This is the delta y. The delta y is what determines how long the ball is going to be in the air for. If it's a very, very high table, the ball will take a longer time in the air. If it's a short table, the ball will be in the air for a shorter amount of time. And so I'll use the delta y equation, this equation right here, to find t. Okay? So I'm going to now say, I'll do it over here. I'll move this over a little bit. I'll say delta y equals, okay, what is the delta y? This is 5 meters high, but look, the ball goes, when a ball falls, it goes down 5 meters. So I need to call delta y -5. Okay, this is -5 because it goes down. So I'm going to say -5 equals, all right, well, let's look at this term right here in the equation. What is the initial y velocity? Well, the ball is coming off the off the table horizontally, so it's got horizontal speed. So when it leaves the table, it has no y velocity. Do you see that? The ball isn't going up or down initially when it rolls off the table, which means this term right here is 0. And if you multiply, it doesn't matter what t is, right? If you multiply anything by 0, you get 0. So this whole thing disappears, and we're left with delta y equals 1/2 gt squared. So -5 equals 1/2 -9.8 t squared. Okay? So I say -5 equals, multiply 1/2 by -9.8, I get -4.9 t squared. And then if I keep going here, I'm going to see that t, I divide both sides by -4.9, so I get -5 over -4.9. That's t squared, right? So then how do I find t? I have to take the square root of both sides, right? So t equals, if I go ahead and take the square root of this side and this side, I get that t equals the square root of this thing. And this is pretty close to 1, so I'm going to get about 1 second. -5 divided by -4.9, that's pretty close to 1, and the square root of 1 is 1. So I'm just going to say that's 1 second. And now I can go ahead and plug in 1 second in here. And I get that 8 equals v times 1, or v equals 8 meters per second. Final answer. Okay? And this method that we went through, hopefully you followed it. You'll see this happen over and over again, where we will frequently use the y to find time. That's a common theme. Let's try a different problem. Let's say we have the same ball, right? So it's rolling off a table again at this speed. So in other words, this next problem, we're going to know that the initial velocity is 8. But let's say it's a different table that this ball rolls off of. So I have a new table now. Here's this new table, and it's higher than the old table. Okay, but the ball's going to roll off the table. Here's the ball again, with the same velocity it had before. So it's going to go 8 meters per second. So the rolling speed here is 8. And it's going to fall over this delta y. And now in this problem, I don't know what delta y is. That's ultimately what I want to look for. I don't know how high this table is. But I do know that the ball falls in this trajectory, which I'm incapable of drawing. And the delta x it travels, the horizontal distance the ball travels now, is 20 meters. It was 8 last problem, and now it's 20 meters. And now I want to know delta y, right? So just to remember the equations, I'll put the equations, maybe I'll put them right here. Delta x equals v sub x times t, and delta y equals v initial y times t plus 1/2 gt squared. Those are my two equations. And I'm looking for delta y, right? Which means I'm going to need to use this equation. I'm going to say delta y equals, okay, once again, this is a horizontal table. The ball is coming off the table horizontally, so this whole term becomes 0. So I get delta y equals 1/2 gt squared. All right, well, to know delta y, I know what g is, right? That's 9.8, but I don't know t. So this is a different kind of problem, right? Because now I've got to find t to figure out delta y. Last problem, we used delta y to find t, and now I'm doing the opposite. Well, how do I find time? Let's look at this equation. I know delta x, that's 20, right? I know that. And I know the v sub x, that's 8. So I can use this equation to solve for t. I'll do that over here. So I'll say 20 equals v, which is 8t. So t equals 8 divided by 20. And what is that? That's 2.5 seconds. All right. So now I know the time. I use the delta x to find the time. And so I can plug this value in here, right here. And I can say delta y equals 1/2 negative 9.8 times 2.5 squared. I'm going to break out the old calculator here. So we can do this out. So what do? I have to take 1/2 negative 9.8 times 2.5 squared. So I'm going to say 2.5 squared times 9.8, and I'm going to have to divide that by 2. Divided by 2, and I get, what is that, 30.6 meters? Now it's negative, right? Because I should have, I made a little bit of a mistake here. I didn't make the 9.8 negative when I plugged it in, but if I had, that would have been negative, right? Let's do that again. How do you do that? 2.5 squared times negative 9.8. I was going to say 9.8, and I think this will make it negative. Okay, and then divide that by 2, and I get negative 30.6 equals negative 30.6 meters, which makes sense because it's falling down, right, again, so this should be negative. So that's my delta y final answer, equals negative 30.6 meters. Okay, so those are two sample problems where we use our two equations. Here are our two equations, 1 and 2. We use these, and we're going to be using these a lot this chapter. We use these two equations right here to solve a variety of problems. And the equations just come out of these two rules for projectile motion. Okay, hopefully that made sense. I'm going to post this video and give you a couple practice problems that you can work on for next class.